Okay, so what I want to do is talk a little bit about the solver.
You're not on the screen.
Thank you. Okay. This would be nice if I could actually like run things on this. Then.
I haven't gotten quite powerful enough for that yet.
No, it's not that. It's I don't have administrative access to this.
Right.
And so it
you
won't.
Can't just put an executable on
So it won't let me run a executable that was from unknown, randomly compiled.
It could have been anyone.
Yeah. So yeah, make sure that you run it under administrative privileges, right? So that command click on Windows, run it as administrator. Okay, so we have VPSC, right? So that stands for viscoplastic self-consistent. Consistent plasticity. Okay, so that means there's no elasticity here, right? So the assumption is that we're going to large strains, and so the elastic strain is very small compared to the applied plastic deformation. Okay, so how does this actually work? Well, so we give it a well, before we do that, what does our input look like? Our input to this is basically a list of grains. Right? And that's specified by their orientation and volume fraction. Right? How big it is, right? You can just take this right from EBSD, right? You get the orientation of the grain and the weight in its area in either pixels or an absolute size, depending on how you calibrated your EBSD scan, right? And you can just put those weights in directly, right? So one of the advantages of this is it's very simple. You don't have to create a finite element mesh, right? You just take data in a very simple form. And then you also have to give it, and you also have to tell it what phase it is. We'll have too many fees. So you have to tell it what phase, right? So that you know what slip systems, what deformation modes will be active, right? And you can set that for however you want, right? There's a properties file, right? You can tell it, I don't want you to use basal slip in this HCP material. Okay. So then we have to apply our boundary conditions, right? And these can be mixed. You give it components of the velocity gradient tensor, and you give it components of your stress, right? So in this case, I say we're doing compression, and so I force, make sure I'm going through it the right way. Okay. So first off, I say don't allow any shear. So we force the off-diagonal terms to be 0. And since it's compression, I give it -1 here. And then these are undefined, right? I don't enforce my axial strain. All I do is I say, overall, I'm going to be compressing at this given rate, right? And then the stress, I have to, the terms that are not specified in terms of displacement, I have to specify them in terms of stress. So right? I specify my stress as a form like this, where I say there's on average, there's no stress in the transverse directions, right? So what kind of test does that correspond to in real life?
There's no what?
There's no stress in the. All right, what's that?
Tensile?
It's not tensile because I've got a negative. What's that? It's not plane stress, right? This is just a simple compression test, right? I've got free surfaces on the sides, right? There's no force resisting expansion out this way as I compress down, right? Okay, so this is what the average over all the grains are going to be, right? But individually, each grain is going to have a triaxial stress state.
Looking at the project problems, it looks like the 3-3 component of the L that you have there is +1 in the document.
Okay, so then, yeah, I'll make sure it's consistent. Okay, so this could be plus. So that would be just a simple tension test. Right, and the same way, this is the average over all the grains. Has to meet this form. Okay, so that's the boundary conditions. So the next thing we need is a constitutive model. Right, and for our crystal plasticity, we basically say our kinematics are right. We start with the assumption that we have our deformation gradient can be decomposed as an elastic part and a plastic part. We're assuming the elastic part is identity. All right, and so and our velocity gradient tensor is the sum over all the slip systems of the shear rates, right? So to get our deformation rate, we just sum up all the shear rates of all the slip systems, right? So this is our kinematics. We need to somehow relate these shear rates to stress, right? And we do that through the power law model that I mentioned in the lecture notes. All right. This is the sum over. And how to, yeah. All right. So let's think about this. This here, this is our Schmidt tensor. Oops. There's no C. So this is our Schmidt tensor, right? This encodes our slip systems, right? This is, right, slip plane. This is the slip direction. Right, this is the slip plane normal, right? So what all this is, right, this is the projection of this stress onto the slip plane along the slip direction, right? So this is the resolved shear stress for the slip system, okay? And this is the critically resolved shear stress for the slip system. I apologize for having multiple M's here, but it's just the stupid notation that we use. Um,
What?
so I've got a, because I use m here to say this is the common notation for the slip tensor, but then I have an m here,
Yeah.
right? This is the strain rate exponent. This is,
Okay.
right, m is very small, 10 to the minus 2, right? So that means this whole thing is raised to some power. Ideally, we'd like it to be like 50 or 100, right? Something large. So what happens when this is, I've got something raised to a large exponent, right? What happens if my resolved shear stress is slightly less than my critically resolved shear stress? Right? I've got a fraction here that's slightly less than 1. A fraction that's slightly less than 1 raised to the 100th power is about 0. Right? This goes to 0 very quickly if this is less than the critically resolved shear stress. What if this is slightly larger than the critically resolved shear stress? It blows up really quickly. Right? And if this is exactly 1, our shear rate is given by this term. This whole thing becomes 1. And so our shear rate becomes this reference shear rate. Right? So this is just a model parameter that that tells you how fast your system, how fast your slip system deforms when this is exactly 1. Right? So this exponent here, right? If this is smaller, say this is now 1 over 10, right? This doesn't go to 0 and infinity as quickly, right? So what that has the effect of is rounding this initial, what would be the elastic plastic transition, right? You get plastic flow initiating over a wider range of stress values, right? When so this is m 1 over m, say approximately 10, 1 over m approximately 50, right? You get a very sharp, right? You have very little plastic flow below that exact activity. So there's lots of different ways we can solve this equation, right? One, the most common way is you put this in a finite element framework, right? And you use finite elements to solve for stress equilibrium, right? But notice that we've got a velocity gradient that's a function of stress, right? But it's a function of stress raised to some very high power, right? This is a very stiff system of equations to solve, right? So it's quite, numerically, it's quite tricky, right? So if you think about, if I give you a velocity gradient like I do, right? And I'm asking you to break it up and find the stress, that when I find the shear rates over all the slip systems and then average it over all the grains, gives me this velocity gradient exactly. Right? It's tricky. Even if I give you the velocity gradient for the grain, right, and say find the stress, it's a really stiff, right? If you plot your error, right, and this is the true value, this is the correct stress, right? If you plot your residual, right, it basically looks like this, right? So numerically, right, you've got a shallow gradient when you're far away and then you've got a insanely steep change, narrow window where you've got a useful gradient to search along, and then you've got a really, it numerically it's a pain right in the rear. So one of the earliest, I guess, would say, polycrystal solvers from I guess I would say they're really contemporary. Crystal plasticity finite elements was kind of developed in the early 90s. VPSC was around the same time. VPSC was a lot faster. But the way it works is pretty cute. So basically, so from structure, right? Structure and dynamics. So imagine you have a kind of this infinite body, right? And do you remember, did you guys talk about the eigenstrains of shear transformations?
No.
Really?
Yeah.
So you didn't learn how to solve for the stress with Martensite? Okay, so is anyone familiar with the classic? Has anyone taken a theory of elasticity course from mechanical engineering or civil engineering? Okay. Is anyone familiar with the classical Eshelby inclusion problem? Okay, so I will give you the really quick rundown of this. Okay.
This is why I want you to go over shear transformations.
So we will talk about this in detail if we do shear transformations. Okay, so imagine I have a 3D body. I'm just going to draw it as 2D, but really this is 3D. And I have something that undergoes a volumetric transformation. Right? No, there's a volumetric strain. So I go through a phase transformation or something, and my volume is not the same. Right? So now I have this little region here of a new phase with a different volume, and I want to know what the stress in here is and the stress in the surrounding area is. Right? The thought experiment that Eshelby did was he said, let's break this up into two parts, right? He actually did this for thermal expansion, right? So say I have two materials with differential thermal expansion, and I heated this block up, right? But we can think about it in terms of phase transformation. It works out the same. So he imagined this in two parts. He said, or in a couple steps, right? Cut out the region. Right, so now I've got a void where it was, right? And I have my regions separate, right? Then perform the transformation, right? And then squish it back into place, right? Squish it back to the original shape and volume, and put it back in here. And then let it relax, right? So then remove your external forces that are squishing it back into place and allow these things to balance out. And it turns out that this actually has a remarkable solution. I'm not going to go through the solution itself, but the form of it is interesting. So if we do this and we assume everything's elastic, what does the stress look like in this inclusion? Does anyone have any sense? It's compressive, right? I mean, if this, right, but, right, it depends on, well, it could be tensile compressive depending on what the volume change was, right? But it turns out that the stress in the inclusion is uniform. It's homogeneous in the entire ellipsoid, right? And in the medium, it decays as a function of distance, right? And so you have a I can never spell homogeneous. U-O-U-S. Right. And so this is the basis of the Eshelby, right? The famous Eshelby inclusion problem. And to solve this, he derived something called the Eshelby tensor, which allows you to relate to work through this. But that's kind of getting beside the point. What we do in VPSC is we do the same thing. The grain is an ellipsoid embedded in a effective excuse me, an effective media, and this medium has the properties of the average of the average polycrystal. All right. So the properties equal that of the average. Okay. Grain, effective medium. All right. But we don't know what the properties of the effective medium are, right? And we don't know what the properties, we know what the properties of the grain are, but we don't know what the response of the grain is. So we have to solve this iteratively. Okay? Basically, what VPSC does is we start with a guess. We start with a guess of what our effective medium is. Then solve instead of an elastic, we solve a viscoplastic Eshelby problem. Right? So we treat the grain as an Eshelby inclusion in this effective medium. Right? So we solve the Eshelby problem. Right, and that gives us, we end up with the stress in the grain and the strain rate in the grain. Right, we use, instead of elasticity, right, we have right, so we, in the elastic region, you have an elastic modulus. We transform the problem so we have a instantaneous plastic modulus. Right? And so we solve the problem as if it were a pseudo-elastic problem where you have a pseudo-nonlinear elastic problem where you've got this instantaneous tangent modulus. But that's a little too deep. I don't want to get lost in those kind of details. Okay, so now we've got a guess of the stress and the strain rate in each grain, and we have a guess of the elastic or effective medium. We use all of the grains, we average them together to get new properties for the effective medium, right? Solve for the grain stresses again and strain rates. Plug it back in, right, until it converges, right? And then we go to the next strain increment, right? And we do this for each strain increment. So the output is basically a stress and strain for each grain, and the orientation for each grain at each time step, right? So you can track how the texture evolves. We're not doing that in this for this homework, but we easily can. Okay, so when